Welcome to This Explainer. Today we are diving into a really fascinating chemistry case study from Lesson 8.3. We're going to see exactly how scientists take everyday claims and put them to the test. Literally. We'll unpack how an experiment is built from the absolute ground up, how data is collected, and, honestly, the most important part, how we should interpret that data when things just don't go according to plan. It's a journey from a vague, everyday question to a hard, rigorous scientific conclusion. So, let's jump right in.
Okay, picture this. You've got terrible heartburn, you walk into a pharmacy and you see rows upon rows of indigestion remedies. How do you know which medicine actually works best? I mean, every single box claims to be the absolute most effective, right? But how do you either as a consumer or, better yet, as a scientist, make that call? Is it based on hard facts, or are we all just falling for flashy marketing, brand loyalty, and, heavily biased opinions? Because let's be real, manufacturers want us to buy their stuff, so their definition of best might be a little skewed. So, to get a real, factual answer instead of just an opinion, we have to completely rewrite the question. If you ask a scientist, hey, which is the best indigestion remedy? They're going to immediately tell you that best is a terrible measurement. What does that even mean? Most pleasant tasting? Cheapest? Coolest packaging? We have to shift from which is best to something strictly testable. Something like which indigestion powder neutralizes the acid using the least amount of powder. Now that is something we can actually measure, totally free from all that marketing spin.
But hold on a second. Before our student scientists for this case study, Marcus and Arun, can start mixing chemicals and testing things, they have to establish the rules of the game. They need to identify their variables. In any scientific investigation, a variable is simply a thing that can change. It's the absolute bedrock of a fair test. If you don't control your variables, you absolutely do not have a fair test, and your results? Basically useless. Think about it. You wouldn't know if your powder worked better because it's genuinely a better powder, or just because you used way more of it, or maybe you used a completely different, weaker acid. It'd be chaos.
It is so important to carefully plan the setup before touching a single piece of equipment. You have to ask vital questions about the procedure. What exactly do we need? How are we going to stay safe? And how will we reliably know when the powder has actually neutralized the acid? In a proper, rigorous scientific investigation, you only ever change one variable. In this case, that's the type of powder being tested. Everything else, like the volume and concentration of the acid, has to stay completely identical. Seriously, that is the only way to ensure the results actually mean something.
All right, let's break down Marcus and Arun's exact game plan. Obviously, if you're testing an indigestion remedy, you can't exactly experiment using someone's real stomach acid. That would be, well, completely unsafe and totally impractical. So they brilliantly use a chemical model instead. They take 20 cubic centimeters of hydrochloric acid, which has a pH of 1, closely mimicking the strength of human stomach acid. To track the reaction, they add a few drops of universal indicator. This is super convenient because it'll turn green the second the acid is perfectly neutralized. Then comes the really careful part. They add the indigestion powder, just one spatula at a time, meticulously counting each one until the liquid hits that green, neutral state.
Okay, drum roll please. Let's talk about the results of their very first experiment. They tested 3 different remedies: powder A, powder B, and powder C. Remember, they kept the amount and type of acid exactly the same for each test to keep things perfectly fair. Now listen to these differences. Powder A took 10 spatulas to turn the indicator green, but powder B, that took only 6, and powder C took a whopping 24 spatulas. I mean, the variation between these remedies is just massive right out of the gate.
So, thinking about these initial numbers, if our goal in this scientifically rewritten question is to find the remedy that uses the least amount of powder to get the job done, well, the choice seems kind of obvious, doesn't it? Take a second to really digest that. We want efficiency here. We're looking for the maximum neutralization power with the minimum amount of product. Based on this single run, one powder clearly stands head and shoulders above the rest of the pack.
Yeah, powder B definitely looks like the clear winner, requiring just 6 spatulas compared to 10 or 24. A real game changer. But wait, is one single test really enough? Good scientists never ever rely on just a single attempt. A single test might contain a fluke, right? Maybe one of the students miscounted, or there was a slight error in measuring out the acid. When you only test something once, you leave the door wide open for random chance to just completely ruin your findings. To be absolutely certain, you need robust, repeatable evidence that proves your initial finding wasn't just a lucky accident.
So, to be totally sure, Marcus and Arun repeat their investigation twice more. And honestly, this is where the scientific method really shines. Listen to how consistent powder A is across 3 separate tries. 10,
9, and 11. That gives us a solid mean, or average, of 10. Powder C is similarly consistent, coming in at 24, 23, and 25. The results are grouping tightly together, which is exactly what we want to see, but pay very, very close attention to Powder B's repeated trials. Something there doesn't quite line up, does it?
I want you to put your detective hat back on for a second and think about this new data. Do you spot a glaring anomaly? Something that completely breaks the pattern established by the other attempts? Because when you look across the results of a well-executed experiment, the numbers should be cousins, if not siblings. But in this case, we have a number that feels like it belongs to an entirely different family altogether.
Yep, you guessed it. It's the number 6. That very first try of just 6 spatulas for Powder B is completely, wildly out of line with the 17 and 16 they recorded on their later attempts. In science, we call this an anomalous result. It's a data point that heavily deviates from the rest of the pattern. It's essentially waving a giant red flag, shouting that something in that specific trial went wrong. It's the outlier, and it demands our immediate attention.
And boom, this illustrates a massive challenge in scientific investigations. What on earth do you do when you encounter an anomalous piece of data? Marcus and Arun originally calculated the mean for Powder B as 13. They got that by adding 6, 17, and 16, and then dividing by 3. But here's the catch. By blindly including that weird number 6, they drag the overall average way down. It makes Powder B look far more effective than it actually is. If they had recognized the anomaly and only averaged the 17 and 16, their mean would be 16.5. Actually, think about that. It completely changes the conclusion of the entire experiment.
You see, you can't just blindly crunch numbers in a spreadsheet. You have to critically evaluate your evidence. When you spot an anomaly, you have to stop and ask why it happened. Did someone accidentally use a heaping spatula instead of a carefully leveled one? Was the acid poured incorrectly for that specific beaker? If you strongly suspect a procedural error happened during that trial, standard scientific practice often says you should just exclude it from the mean so it doesn't artificially skew your final results. Bottom line, including bad data leads to bad conclusions.
Which brings us to our final takeaway from this incredible lesson in the scientific method. The next time you see a bold claim on a medicine box or even a polished data table in a fancy report, are you just going to accept it at face value? Or will you ask to see the variables? Will you ask to see the repeated trials to verify consistency? Because true understanding doesn't come from just reading the final average. It comes from critically questioning how that evidence was gathered in the first place. So the next time you see a scientifically proven claim, will you just trust the average, or will you ask to see the anomalies?